Welcome to Deep Dive Lab, where we break down and dissect cutting-edge scientific research. We cover everything from advanced biomedical technologies to breakthroughs in AI, materials science, chemistry, physics, all told as compelling, easy-to-follow stories.
Yeah, and today we've got a really incredible story.
We really do. Today we're taking a deep dive into something that honestly sounds like pure science fiction,
Yeah,
but I assure you it is very real.
it definitely is.
But before we get into the quantum realm with all this, I want you to picture something highly relatable. Just imagine you are at the beach, right? You've paddled out on a surfboard and you're just sitting there waiting for that perfect, smooth, glassy wave to ride in.
Oh yeah, I mean that's the classic surfer's dream, right? You want that organized, uniform swell where all the water is just like moving together in one constructive direction.
Exactly. But instead of that perfect wave, the ocean you're sitting in is just an absolute mess. It is chaotic, it's choppy, waves are crashing into each other from the left and the right, water is splashing in literally every random direction, and it is completely unpredictable.
Yeah, you definitely can't ride that. I mean, the energy is it's powerful, but it's totally disorganized.
Right. Because the energy is scattering rather than moving in a unified cooperative way.
Yeah,
It's just noise.
exactly.
Now, here's a strange question for you. Why does so much of the sun's energy just turn into useless baking heat the second it hits a solar panel on your roof?
That's the million-dollar question.
Right. Well, it turns out sunlight hitting a solar cell behaves exactly like that chaotic, choppy ocean. The immense energy is there, but at the quantum level, the light is a disorganized mess. But what if you could drop a microscopic bouncer into that chaotic ocean to force those erratic waves to just, line up and behave?
Which sounds impossible, but
Right, but scientists have actually just figured out a way to do exactly that with light.
and, you know, this represents a monumental shift in physics and materials science. Because to understand why this is such a big deal, you have to look at how we've historically interacted with light.
Okay, set the stage for us.
So for decades, even centuries, science has mastered certain properties of a light wave. Like we are really good at changing its color, which is just altering its frequency.
Right, you just do that with a simple glass prism.
Exactly.
Oh.
And we're also incredibly good at changing its direction, which is its polarization. You experience that level of mastery literally every single time you put on a pair of polarized sunglasses on a bright day.
Oh, sure. The lenses just, block the light waves that are bouncing in certain horizontal directions to cut the glare off the water or the road. So we've got color and polarization completely under control.
We do. Those are solved problems. But there is a fundamental property of light that has been essentially untamable for, well, as long as we've been studying quantum mechanics.
Untamable how?
It's called quantum coherence, or the statistical fluctuations of multi-photon systems.
Okay, let's unpack this. Statistical fluctuations.
Yeah, basically this describes the tendency of photons, the individual microscopic particles of light to either clump together in packs or push apart from one another as they travel.
Wait, hold up. So we've been building lasers and fiber optic cables and solar panels for decades without even being able to filter the basic, social dynamics of the photons.
That is exactly what has been happening, yeah. We haven't been able to passively filter them because until now, there was literally no material on Earth intrinsically sensitive to the quantum statistical properties of these multi-photon systems.
There you go.
Right. Unlike polarization, where you can just put a simple static filter in front of a beam of light and watch what passes through, you couldn't do that with quantum coherence.
Why not, though? Why is it so much harder to filter a clump of photons than it is to filter their color?
Because to even identify these statistical properties, how the photons are interacting with each other, scientists had to measure the entire collective behavior of the light after the fact. We're talking about something called second-order coherence.
Wait, hold on. Second order? What happened to the first order? Are
Yeah.
we just throwing math jargon around, or does second order actually mean something specific here?
No, that's a very
Wow.
fair question. First-order coherence is just about the predictability of a single light wave interfering with itself. Think of the famous double slit experiment, where a single wave overlaps and creates a pattern.
Okay, yeah, we understand that well.
Right. But second-order coherence is about the relationships between multiple particles. It's the correlation of intensity. Like, are these two photons arriving at the exact same time? Do they avoid each other? It is strictly about their group behavior. And because you're dealing with group behavior, you couldn't just filter it on the fly. You had to catch the photons at the very end of their journey, literally destroy them in a detector, and then do all the math to figure out how they had been acting beforehand.
So it's almost like trying to figure out if a crowd is rowdy by waiting until the concert is entirely over, analyzing the damage to the seats, and running statistics rather than just having a bouncer at the door, checking IDs and turning away the troublemakers.
That is a perfect way to conceptualize it. You just couldn't check them at the door. And because a light wave's quantum statistics are incredibly fragile and chaotic, just trying to hold on to these multi-photon quantum states to study them or use them was an absolute nightmare.
Fragile how? Like they just fall apart if you look at them wrong.
Almost literally. Any environmental noise, even just the microscopic vibrations of atoms at room temperature, can bump these photons and completely ruin their delicate social structure. It's called decoherence.
Oh, man.
Yeah, so to keep these delicate states from falling apart, scientists have had to rely on massive freezing cryogenic environments. If you've ever seen a picture of a quantum computer, it looks like a giant gold chandelier, right?
Yeah, those big, complicated-looking steampunk things.
Exactly. Well, that whole structure is practically just a giant refrigeration unit designed to cool the system down to a fraction of a degree above absolute zero.
Just to keep the atoms still so the photons can behave.
You got it. You had to freeze the entire environment so the crowd wouldn't get rowdy.
Okay, so if freezing them in a giant chandelier is the only way to keep them in line, how are we supposed to actually use this stuff in the real world?
Yeah.
Like, we obviously can't put a cryogenic freezer on a solar panel on someone's roof. So how did scientists figure this out without a deep freeze?
Well, this is where the story gets incredibly exciting. We are looking at a groundbreaking study that was published in the journal Nature in July of 2026. The research was led by Dr. Shenglong Yu, Dr. Omar S. Magana Loaiza, and their colleagues at the Quantum Photonics Laboratory at Louisiana State University, alongside researchers with ties to the University of Electronic Science and Technology of China.
So what exactly did this team at LSU build to finally act as a bouncer for light?
They engineered an entirely new type of material. It is called a quantum statistical plasmonic metacrystal.
Wow, okay. That is a mouthful. Quantum statistical plasmonic metacrystal. It sounds incredibly intimidating, honestly.
I know the name is intense, but when you look at the physical geometry of what they actually built, it is surprisingly elegant.
Okay, paint a picture for us. What does it look like?
Well, the visual imagery of this invention is stunning when you zoom in on it with an electron microscope. Imagine a remarkably thin, perfectly flat piece of glass, a substrate about 175 micrometers thick.
Pretty thin.
Very thin. And on top of that glass, they deposited an ultra-thin layer of gold. And when I say ultra-thin, I mean just 110 nanometers thick.
Okay, to give you all a sense of scale, a single human hair is about 80,000 to 100,000 nanometers thick. So this gold layer is unimaginably thin. It's practically two-dimensional.
Exactly. But the magic doesn't happen just because there is gold. The magic happens in what they carved into that gold film.
What did they carve?
Using advanced lithography, they etched 100 tiny nano antennas into the gold. Each of these rectangular antennas is only 200 by 400 nanometers in size, and they're arranged in a grid spaced exactly 1 micrometer apart.
Okay.
In the realm of metasurfaces, these tiny carved antennas act as meta-atoms. Basically, they are synthetic atoms designed to interact with light in highly specific ways.
It kind of sounds like a microscopic gold Plinko board. Yep. But instead of bouncing little plastic chips down a pegboard, it's organizing light. But here's where I get a little stuck.
Yeah.
A piece of gold with holes in it is completely static because it doesn't have moving parts.
Okay.
How does a static bump of gold actually push a particle of light around to change its behavior?
That is where the word plasmonic from the title comes in. When light hits this gold Plinko board, it doesn't just bounce off like a mirror. The light actually decouples with the free electrons on the surface of the gold.
Oh, interesting.
Yeah, it creates something called a surface plasmon polariton.
So the light kind of temporarily turns into like a ripple of electrons.
Precisely. You can think of it like the light wave melting into a fluid wave of electrical energy that literally ripples right across the surface of the gold.
Oh, wow.
And as this plasmonic wave flows, it crashes into those tiny meta-atoms, the antennas they carved. The physical shape, size, and spacing of those antennas force the electron wave to navigate a highly specific obstacle course.
Kind of like a maze.
Yes, exactly. And this creates complex interference patterns. The ripples crash into each other, canceling out in some places and amplifying in others.
And then once it navigates the maze,
It re-radiates. It just turns back into a wave of light on the other side of the glass.
okay, that actually makes sense. The light becomes a fluid, gets molded by the physical trenches of the gold, and pops out the other side changed,
Yeah.
So how do you even test something like that to see if it works as a statistical bouncer? Like, do they just shine a regular laser pointer at it?
Not quite. A standard laser wouldn't give them the data they needed. They had to design a highly rigorous experiment.
Hmm.
They actually generated and fired 13 distinct types of multiphoton light fields at this gold grid.
Wow, 13.
Yeah, and they ranged the light from perfectly uniform, laser-like coherent light all the way to highly chaotic, super thermal light, which is incredibly noisy and clumped together.
And to measure what was happening on the other side of the crystal, you can't just use a normal camera, right?
No, absolutely not.
Yeah.
A normal camera just records intensity or brightness. To see the social dynamics, they used specialized equipment called photon number resolving, or PNR, detectors. These are incredibly sensitive devices that can actually count the individual photons as they arrive. So by counting how many photons hit the detector in any given nanosecond, they can see exactly how they are clumping together or pushing apart after they pass through the metacrystal.
Ah, so they're measuring that second-order coherence we talked about.
Yes, got it.
Okay, so they shoot 13 different types of light through the gold Plinko board, and they count the photons on the other side. What'd they actually find?
This is where the paper really shines. When they measured the light coming out the other side, they found that this gold crystal had created allowed and forbidden statistical bands.
Like a band gap.
Yes. Think about how a semiconductor inside your computer has band gaps that allow or forbid electricity from flowing based on its energy. This crystal was doing the exact same thing, but for the statistical behavior of light.
Wait, so to use the VIP club analogy we were talking about earlier,
Yeah.
if the light has an allowed statistical value, the crystal simply lets it pass through perfectly unbothered. Like, if you're on the list, you walk right in.
Precisely. For example, coherent light, which has a statistical coherence value of 1, is on the VIP list. It passes right through the crystal, completely unmodified.
Nice.
And thermal light, which is slightly more chaotic and has a value of 2, is also on the list. Super thermal light, with a value of 3, passes freely as well. If you have an allowed coherence value, the plasmonic field just lets you re-radiate exactly as you were.
But, okay, what happens to the forbidden light? Like, if a light wave shows up and it's not on the list?
So let's say a light field hits the crystal with a forbidden coherence value of 2.15. It is definitely not on the VIP list.
Does the bouncer just block it? Like, does the light just reflect off?
That is the truly amazing part. No, the metacrystal actively forces it to change its identity.
Wait, what?
Yeah, the light gets thermalized. Because the incoming light doesn't fit the allowed pathways, those complex interference processes mediated by the gold meta-atoms physically push and morph the light's quantum statistics until it reaches an allowed band.
That's wild.
Right. So that forbidden light coming in at 2.15 gets squeezed and pushed by the geometry until it exits the crystal at an allowed value of 2.58.
Hold up, so it rewrites the identity of the light so it can get in?
Yeah.
That almost sounds like it breaks the rules of physics. It just forcibly dictates the social dynamics of the photons?
It does. And they saw this happen across the board. Like, if a subthermal field of 1.25 hits the crystal, it gets shifted and exits at exactly 1.50. The researchers proved that you can engineer these statistical bands entirely deterministically.
But how does the crystal know what the allowed number should be?
It all comes down to the physical geometry we talked about earlier.
The size of the antennas?
Yep. The size of the nano antennas, those specific 200 by 400 nanometer dimensions dictates the baseline allowed coherence values. That size essentially sets the guess list.
Okay, got it.
But the orientations of those antennas, the angles at which they are carved relative to each other and their collective arrangement in that 100 antenna grid, that controls the bandwidth. It controls the width of the forbidden gaps.
So if you carve them at different angles, you get a completely different VIP list.
Yes. Meta-atoms that are aligned in the exact same direction create indistinguishable multi-particle interference. But if you orient them differently, they produce distinguishable effects, which alters how the electron ripples crash into each other.
Oh, wow.
By carefully designing this physical geometry in advance, they literally engineered a material that passively filters and forces quantum statistics just by sitting there.
Okay, so we have a microscopic gold bouncer that fixes light's social dynamics just by sitting on a piece of glass. Which, I mean, that is a fantastic party trick for a university physics lab. But why are they doing this? Who actually needs this level of control over photons?
Well, the real-world implications are massive, and they start with something that affects absolutely everyone: energy.
Okay.
Let's circle back to your opening analogy about the choppy ocean and the solar panels on your roof.
Right, the useless heat problem. The sun hits the panel, and instead of giving us electricity, a huge percentage of it just heats up the roof. Why does it do that?
In standard solar panels, the sunlight hitting the silicon-absorbing material is only partially coherent. It's statistically chaotic.
Right.
Because of this chaotic nature, the light experiences a quantum phenomenon called Anderson localization.
Anderson localization, what's that?
Basically, because the light waves are disorganized, when they hit the complex atomic structure of the solar panel, they destructively interfere with themselves. The energy essentially gets trapped or localized in random pockets of the photovoltaic material.
Oh, so it can't flow smoothly to the wires.
Exactly. And when energy gets trapped and localized like that, it just makes the atoms vibrate.
And vibrating atoms means heat.
You got it. It turns precious optical energy into wasted heat instead of electricity. The chaotic statistics suppress the long-range transport of that energy.
But we can put this metacrystal in front of the solar panel.
Exactly. Because this metacrystal operates entirely at room temperature, which is the absolute key breakthrough here, it can be used to optimize the quantum coherence of sunlight before it even gets absorbed by the solar cell. It acts as a statistical pre-filter, organizing the chaotic waves into a smooth, usable, allowed state.
So the light hits the gold, gets smoothed out into that perfect glassy surfing wave we were talking about, and then hits the solar panel so it doesn't get trapped.
Yes. This paves the way for hyper-efficient next-generation optoelectronic devices and solar cells. We could drastically reduce the amount of energy lost as heat just by coating the panels with this specific geometric pattern.
That is incredible for energy. But earlier you were talking about quantum computers, those giant freezing chandeliers. Does this apply there too?
Absolutely it does. The fragility of multi-photon quantum systems, the fact that they fall apart at room temperature, has been one of the biggest roadblocks to scalable quantum computing.
Could they just decohere?
Right. Right now, scaling up means building bigger and bigger industrial freezers. But this discovery proves that you can filter, maintain, and transport these fragile multi-photon quantum systems robustly and without distortion at ambient room temperature.
Because the gold crystal does the heavy lifting just by existing. Like the geometry does the crowd control, so you literally don't need the freezer.
Exactly. The researchers noted that this metacrystal enables high-fidelity, constant-time transformations of quantum systems independent of their size.
What does that mean in practical terms?
In simple terms, whether you are dealing with a small quantum system of just a few photons or a massive one with thousands of particles, this metacrystal processes their statistical properties efficiently and instantly. It completely bypasses the need for complex, bulky, freezing equipment to manage the coherence of the light.
It's like taking a supercomputer that used to take up a whole warehouse and required industrial air conditioning in the 1960s, and suddenly shrinking it down to a microchip that just sits on your desk.
That's a perfect analogy.
We are looking at a foundational stepping stone for putting quantum technology into everyday devices.
It truly is a paradigm shift in material science. We went from materials that filter simple things like color or polarization to a material that is intrinsically sensitive to the quantum many-body dynamics of the light itself.
Okay, we have covered a massive amount of ground today, from choppy oceans to plasmonic ripples. Let's distill this deep dive down to the three major takeaways you need to remember.
That's good.
First, scientists at LSU have successfully created the world's first room temperature material that is intrinsically sensitive to the quantum statistical properties of light. It actively filters how photons interact with each other.
Second, the mechanism behind this isn't complex moving parts. It is pure geometry. By arranging microscopic gold nanoantennas into a metacrystal, they created allowed and forbidden statistical bands.
Right.
If light doesn't fit the allowed profile, the crystal physically forces it into a new statistical state by channeling the light through a plasmonic obstacle course.
Which is still just wild to me. And third, this leap is going to fundamentally rewrite two major industries. It gives us a way to pre-filter sunlight, to stop solar panels from wasting energy as heat via Anderson localization, and it allows us to transport fragile quantum computing states at room temperature without the need for massive cryogenic freezers.
Yeah, and if we look at the big picture, what is truly fascinating here is how human understanding and our manipulation of light have evolved.
Definitely.
For centuries, our best trick was just bending light with curved glass lenses. We figured out how to focus it, how to split it into a rainbow, but now we are designing synthetic, microscopic geometries that dictate the very social rules that photons must follow.
Right.
We aren't just directing traffic anymore. We are telling the cars exactly how close they are allowed to drive to one another.
It really is an entirely new level of control over the physical universe. And, that leaves us with a final provocative thought for you to mull over.
Oh, I like where this is going.
In this experiment, the researchers used a static, physical grid of gold etched onto glass. The geometry is fixed. The VIP list doesn't change. But what happens if we figure out how to make those nano-antennas dynamic? What if we could use advanced materials to make them shapeshift or change their orientation in real time based on an electrical current?
Oh, wow. That would mean having tunable statistical bands on the fly.
Exactly. If we can dynamically change the bouncer's VIP list from millisecond to millisecond, could we eventually broadcast complex quantum software right through the open air, perfectly maintaining its fragile integrity through a noisy, warm environment?
It's certainly possible.
Could we one day perfectly control that choppy, chaotic ocean of energy, turning every single scattered wave into the perfect ride?
I mean, it seems the fundamental tools to build that future are finally coming into focus.
They really are. Thank you for joining us on this scientific journey today in the Deep Dive Lab. If you want to keep exploring the absolute cutting edge of human knowledge, make sure to follow and subscribe for more science stories. Until next time, keep questioning the world around you.